Chemical volatility can appear like pure, uncontrollable chaos. But in industry, this volatility serves as a calculated tool. Every time we mix reactive elements, we are making a specific trade, accepting the risk of catastrophic destruction to extract industrial utility. This chart shows exactly how we map that trade-off. We plot risk on the vertical axis against industrial utility on the horizontal axis. We want high utility, but to get it, we often have to push high into the extreme risk zone. Take reaction number 10, thermite. It drops right up here into the high-risk, high-utility quadrant. It's incredibly dangerous to handle, but highly valuable. Mix aluminum powder with iron oxide and ignite it, and you produce a river of molten metal, burning at 2,500 degrees Celsius. That heat is intense enough to slice straight through a solid engine block. But that concentrated heat serves a specific engineering purpose. Railway crews use this exact reaction to seamlessly fuse heavy steel rail tracks together. The danger comes from the atomic mechanics. Aluminum has such an aggressive affinity for oxygen that it violently strips oxygen atoms straight out of the iron. Because the reaction generates its own oxygen as it burns, it fuels itself. That self-oxidizing loop means you cannot put a thermite fire out with water. Hitting it with water just triggers a steam explosion, throwing molten iron in every direction. The utility is high enough that we initiate a reaction we know we can't easily stop. But look at the top left of our chart. This is the extreme risk zero utility zone, and it's exactly where we find reaction number 9, cesium exposed to moisture. The instant cesium touches even trace amounts of ambient moisture in the air, it reacts faster than your eye can track. It generates hydrogen gas and enough heat to detonate that gas in the same millisecond. This happens because cesium has a massive atomic radius. The nucleus is so far away from its outer edge that it has almost no grip on its outermost valence electron. The moment it meets a water molecule, it instantly sheds that electron. Because the reaction is so fast, the rapid pressure wave can shatter the heavy glass ampules scientists use to store it. It creates the physical equivalent of detonating a stick of dynamite inside a sealed water bottle. A reaction might produce immense power, but if the speed and pressure cannot be safely managed, the material has no industrial value. Reaction number 8 looks like a harmless dark brown powder, but once it dries out, nitrogen triiodide becomes a highly sensitive contact explosive. This instability is driven by steric hindrance. 3 massive iodine atoms are physically squeezed around one tiny nitrogen atom. They don't fit, creating unbearable structural tension at the molecular level. The structure is under so much physical strain that the slightest kinetic input, a resting fly, a puff of air, or the touch of a feather, causes the molecule to snap violently apart, releasing a sharp crack and purple smoke. That physical fragility makes it impossible to handle. But reaction number 7 takes aggression to another level. Chlorine Trifluoride was once tested by engineers as an extreme rocket propellant, before being swiftly abandoned. It is so desperate to steal electrons that it spontaneously sets fire to the exact materials we normally use to put out fires. It burns straight through concrete, asbestos, sand, and even ash that has already been burned. Warning tone: industrial application requires boundaries. An element's utility vanishes when it consumes the very infrastructure meant to contain it. Not every explosive reaction requires oxygen. Reaction number 6, known as the barking dog, sends an intense blue light wave racing down a long glass tube, accompanied by a loud woof sound. This is a highly exothermic reaction between nitrous oxide and carbon disulfide. It releases massive amounts of energy and leaves behind a highly toxic, flammable sulfur gas byproduct inside the cracked tube. Reaction number 5, white phosphorus, skips the ignition phase entirely. It reacts so aggressively that it bursts into an unquenchable flame the moment it touches room temperature oxygen. Its 4 atoms are locked in a tight, highly strained tetrahedral structure. When an oxygen molecule hits it, the bonds snap instantly. To prevent severe deep tissue burns, handlers are forced to store it permanently underwater. But white phosphorus still requires air. Reaction number 4, TATP, requires nothing but mild heat, friction, or shock. Bomb disposal experts consider it one of the most unpredictable compounds on Earth. TATP doesn't create a traditional fire. Instead, it decomposes entirely through entropy. Solid molecules undergo an instantaneous expansion into a massive volume of gas, generating a crushing pressure wave. The most unpredictable industrial threats are those that respond to physical pressure and entropy rather than traditional heat or fire. In these cases, the energy required to move the material can also be the force that triggers its expansion. We can evaluate these risks by comparing lethal reactants on the left with the stable, everyday products they create on the right. For reaction number 3, look at explosive sodium metal and pure poisonous chlorine gas. Combined, these two deadly substances yield ordinary table salt. Drop the metal into the gas and you get a violent, blinding yellow flame, as an electron is forcefully transferred from the sodium to the chlorine. Once that volatile transfer finishes, the resulting compound is completely harmless to consume. We see the same risk-to-reward ratio in reaction number 2. Mixing hydrogen with oxygen creates an ear-splitting explosion from a spark, leaving behind only water vapor. In 1937, this exact chemical combination consumed the Hindenburg airship in a matter of seconds, demonstrating the result of uncontained volatility. Yet engineers harness that exact same volatile reaction, channeling the energy output to safely push heavy rockets like the Saturn V upward to overcome gravity. By containing these reactive forces, engineers turn a destructive explosion into a controlled engine. The energy that consumed the Hindenburg is the exact same energy used to push heavy payloads into orbit today. And finally, we have reaction number 1, fluorine. It is so reactive that it will explosively ignite water, glass, solid metals, and even noble gases, all without any external spark. Its power comes from possessing the highest electronegativity on the entire periodic table. A fluorine atom pulls with such overwhelming force that it forcefully tears electrons away from almost anything it touches. The chemists who first tried to isolate it faced severe consequences. Working with fragile glass apparatuses, many were killed, earning the historical nickname fluorine martyrs. Mastering this element's unique reactivity eventually enabled the synthesis of high-performance pharmaceuticals and advanced structural materials that are impossible to create with less aggressive elements. Chemistry is an ongoing calculation. We continually weigh extreme atomic volatility against the essential human utility we extract from it. Drop a comment and tell me which of these 10 reactions shocked you the most. And make sure you hit subscribe, because in our next video, we're measuring the impact of compounds so toxic that a single drop changes the equation completely. Stay curious and stay safe.